All right, everybody. I'd like to give you guys another set of notes. I'm going to call these like alternate energy notes because these might be a little bit more concise and more specific, a little bit easier to understand than the ones that I kind of made from the book. So let's go ahead and get started. At the beginning, it says, what is energy? Simply put, energy is the ability to cause change. So energy causes things to change. So for example, for you to move around, you need some energy from food. If you don't have that energy from the things you eat, you can't move around. So we can change where we are, like our position, if we have energy from food. So that's our change. Throwing something. To throw something, you need to give it some energy. So giving it kinetic energy, and we'll talk about that in a second, for it to move. Burning something, like lighting a fire. Okay? You need to provide some energy for that. So maybe you light some paper and then stick it under like a log in a fire pit. Okay. You need to get some what we're going to call is you're releasing chemical potential energy. And again, we'll talk about that in a second. But you're releasing energy inside of, let's say, the lighter or inside of the paper that you light on fire to get the bigger fire started, right? You're using some energy already to cause something to change. Looking at potential energy. Potential energy is energy that is stored. We say that nothing's changing right now, but it has the potential to cause some change. Okay. Potential energy, if we want to look at how much potential energy something has, we have to look at the object's mass, so how heavy it is, essentially, and its position. So that could mean how high it is off the ground. If you have something that you're like stretching like a rubber band, how far you stretch it, that would be its position. Okay. Typically, when we talk about potential energy, we're referencing gravitational potential energy. Gravitation, meaning like gravity, so how high it is from the ground. So that means our position we're talking about typically is going to be our height. Next one, kinetic energy. Kinetic energy is energy of motion. So things that move have kinetic energy. And if we want to measure kinetic energy, we have to look at the object's mass, so that's the same, and its speed. Right. Now, notice math is in both. So the real thing that's going to give away if something has more potential or kinetic energy is its position or speed. So as a quick check, which of these objects has more energy? A truck weighing 4,000 pounds moving at 30 miles per hour, or a car weighing 2,000 pounds moving at 30 miles per hour. So which of these do we need to check? First of all, it's moving. So that probably tells us that we're going to be looking at kinetic energy. So let's just look at that one, kinetic energy. And notice, let's see, we can look at its mass or speed. Well, its speed are the same. They're both moving at 30 miles per hour. So the speeds are the same. So that's not going to tell us anything about which one has more kinetic energy. So then let's look at the mass. There's a truck that weighs 4,000 pounds and a car that weighs 2,000 pounds. Well, the thing is, if it has more mass, it's going to also have more kinetic energy. Okay, so this one, that 4,000 pounds, tells us that the truck has more kinetic energy because it weighs more. All right, let's take a look at some of these potential energies. So, like I said up here, gravitational potential energy is just one type. We also have something called elastic potential energy, and these are all stored energies. So I'm just going to So elastic energy is stored energy because something is stretched or compressed, or you could say squeezed together. I usually like to think of like a rubber band or a spring in this case. So let's say we have like a spring here. We go ahead and put a force down on that spring. We push it down. That spring now looks like this. It's all nice and compact now. Like think about clicking a pen, right? If I compress that spring in there and then let it go, that wants to change, all right? So by compressing it, you're storing some energy, and then when you let go, you're releasing it. So this would be like this is a spring being compressed. For chemical potential energy, again, it's stored energy in an object because of what it's made of. So I like to think of, for chemical potential energy, like a good example is like gasoline. You know, if you throw gasoline on a fire, you're providing some energy for that fire. You can't just throw any liquid on a fire. It has to be like certain types that are actually going to react. So it has energy based on what it's made of. Okay, there's the stuff, the atoms and molecules inside of it, the bonds that all those things have provide that thing some energy. All right, last one, gravitational. We already said it's stored energy because of the object's height. All right, so for my example for this one, let's think of a ball being held above the ground. So here's our ball. It's falling. Okay, and here's another ball that's just sitting on the ground. Well, it's because of the object's height. If the object has more height, so it's higher off the ground, it's going to also have more gravitational potential energy then. So this ball has more gravitational potential energy than this one because it's higher up. All right, so those were some potential energies. Let's talk about kinetic energy now, a little bit more. Again, kinetic energy has to do with things that are moving. And we can say the energy that a moving object has, we can look at this in two different ways. So we can say because it's moving, it has kinetic energy. We can also say kind of the opposite. Because it has kinetic energy, it's moving. So two ways to look at this, and I think they're both helpful. The first one's saying because the thing is already moving, we can say that it has some kinetic energy. It must have some kinetic energy from somewhere. The other part is saying, well, because let's say I gave this object kinetic energy, then it means it's going to start moving. Okay, so you can look at it two different ways. The reason we were looking up here, we were saying they're both already moving. Okay, so we know they both have kinetic energy. Which one's going to have more? It's this one. All right, so because it is moving, it has kinetic energy. That's how we kind of use that up there. All right, now here is the big point for this whole topic, is something we need to know about total energies. So this thing called the principle of conservation of energy, I'm going to call it PoCoE for short, says that energy is not created or destroyed. And you might have heard that before. That's a very common saying. Let's take a look at what that means. So I just said total energy in an object does not change. To help us think of this, we can think of a pie chart. So here's my little pie chart I have. And the whole pie chart, all 100% of this is the total energy. What's cool about a pie chart, though, is like if you take some from one part, it goes to the other part. Like it's not just, you're not just cutting out this piece and there's a blank spot, right? So as I turn this, we'll see, let's say if we get rid of some of the potential energy, well, that just means it's going to be turning into kinetic energy, or it's going to be changing. All right. So the total energy is not changing, just the different pieces of the total energy. So let's see what that actually looks like on the back. Here's a quick example. So PoCoE says energy can't be created or destroyed, but it can change, and that's the important part. It can be changed. So for example, let's think about a firework. Okay, we have a firework. We're using some chemical potential energy. That's like the gunpowder and the different chemicals inside the firework that make it explode and go up into the air. So what's happening is we have CPE starting off, and then that's going to be turned into, like, as soon as that firework explodes, right? We get all sorts of things, like we get sound energy and light energy. It makes the bang and it's really bright. We'll get some heat energy or thermal energy, as it's called. The chemicals in that firework are what made it go up into the air. So that gave it some kinetic energy. And then once the firework's in the air, and then it starts, like as soon as it stops going upwards and starts falling back down again, some of that's going to be changed into potential energy. Because, well, now it's high up and it's going to want to change and fall back to the ground, so that would be more potential energy. So look at all these ways that energy can go back and forth to different things. All right, let's take a look. I have a problem here, a bouncy ball problem, and I got some scenarios here. So I'm going to take a look at like our little pie charts here, and we're going to kind of see what's going on with this ball that's dropping. Okay, so we have our scenario 1. Our ball is about to be dropped. So let's say we have this ball just floating in the air. It's floating. It's not falling yet. I don't have any lines showing that it's moving. So there's our ball. Here's the ground down here. But what would we say this total energy in this ball looks like right now? So let's go ahead and flip back over. I'm going to look down here, I guess. So between all of these, let's see. I'll look up here, actually. It's going to have more potential or kinetic energy. All right, let's take a look at each of these. So is the ball moving right now? No, I said it's about to be dropped. It's not being dropped yet. So that means it's storing some energy. As soon as I let go of that ball, it's going to fall. I don't have to like throw it down. It's just going to do it on its own. So it's storing some energy there. So we know it has some energy, and that would be its potential energy. So let's go ahead and draw this. In our pie chart, since it's not moving yet, 100% of that energy in that ball is in the form of potential energy. Let me just quickly shade this in. Okay, so 100% of that is potential. All right, scenario 2. Now we got our ball is actually falling. So let's take a look at that now. We have our ball like about here. Get some lines showing it's falling. Okay, that ball. Now it is still off the ground. So remember, if it has some height off the ground, it's going to have some potential energy. So it will have some PE still. But it's also moving now, so it's also going to have some kinetic energy. So let's just take a look at pie chart again. We went from all potential energy, and it started to move, so some of that potential energy is turned into kinetic energy. Let's just say, for the sake of this, it's about halfway down, so let's just make our pie chart about halfway. We could actually figure this out. Like, knowing the mass of the ball and its speed, we could actually just plug it into a formula and get that answer. And we would know for certain how much, like, percent that ball had of potential or kinetic energy. But we're not doing that. We're just going to assume it's something like this. We know that there's not just like a little sliver. We know it's not all kinetic. All right, we're just going to make an assumption and say it's somewhere around the middle. Okay, so that seems good to me. Next scenario, ball hits the ground and is bouncing back. All right, let's draw what that looks like. So we have this ground. One thing you might not know if you've never seen it before is when something like rubbery, like a bouncy ball, hits the ground, it actually stretches out and compresses. Like if you even bounce a basketball, if you have a slow-mo camera on that, it's going to show that ball is actually like squishing together, and that's the reason why it has a bounce. It springs back. So we need to know that the ball is compressed when it hits. Right, so it is compressed, so that means it's storing some energy in that compression. Also want to know that at that time, at this instance, when we take this little picture right here of this ball hitting the ground, at that time, it was moving, my pen is dying, the fastest. Right. Now, you could take my word for this second part, or you can, let's just think about it. Right here at the bottom, the ball is at the ground. So is it going to have much potential energy? If potential energy is usually looking at its height above the ground, well, if it's here, it's really not going to have any potential energy. So let's make our potential energy go almost 0. There we go. That's telling us it's going to have a ton of kinetic energy now. I'm saying it's the fastest. That's because the only energy it has is kinetic energy. And remember, kinetic energy is energy of motion, or we look at its speed. Okay? And remember down here I said these two ways of looking at it. So in this case, I want to look at this side. I'm saying because it has kinetic energy, it must be moving. The more kinetic energy it has, the faster it's going to be moving. So here we go. If it's all kinetic energy, that's going to be the fastest it's ever going to go. So does that sound okay with those statements? In my pie chart then, I want to draw this. For the most part, I'm going to draw it. I'll draw a little sliver of potential energy left, and the rest is kinetic. All right, now this potential energy, I can also say that this little blue spot right here doesn't have to be gravitational potential energy. This could be energy stored, like we said, because it's compressed. This could be, elastic potential energy. It's stored because it's like a springy rubber ball. It's storing some energy. And our last scenario is going to be the ball is bouncing upwards. So let's look at the ball here. Let's say it's right about here. And it's moving upward this time. Right now, what type of energies what's our energies going to look like? So I'm going to again get my trusty little pie chart. We went from all kinetic. Now we're going to start moving up. So we're going higher. So we're going to be gaining some potential energy. And you know that if you throw like a ball like straight up into the air, it can only go so high before it stops completely and then turns back around and starts falling down. That's because as it goes up, it's losing kinetic energy. If it doesn't have as much kinetic energy, it's not going to have as much speed, so it's going to slow down. Okay, so if we go from all kinetic to having some potential, we're slowing down. So again, for the sake of this, let's just say this is half and half for my pie chart. Potential, kinetic. All right, does that make sense?